numerous startups. The working team leading his research is pragmatic approaches to fundamental research. This includes making use of principled approaches to develop new practical ML tools and studying theoretical questions empowered by real-world applications of ML. Yaring has published in many different fields, from Bayesian deep learning, adversarial machine learning, quantization and training, active learning, Bayesian non-parametric scalable MCMC, and so on. And the applications of all of these methods include computer vision, medical analysis, astronomy, autonomous driving, finance, natural language processing, robotics, etc. You can look at his webpage for having access to a lot of his publications. So thank you very much, Yaring, for being here, and you can start your talk.
Thank you.
You have the microphone. No? Okay.
So can you hear me at the back? Do I need to use this? Okay, I'm not going to use it. Mute. Okay. Yeah, so thank you for the invitation and for the opportunity to give the talk over here. So today I'm going to talk about intersection of Bayesian deep learning and space applications astronomy. I'm going to say in advance that I'm not an expert in astronomy. I've had the fortune of collaborating with some really good collaborators in the field and having done a bunch of really fun projects. That's what I'm going to talk about today. My main field of expertise is more the machine learning side, Bayesian deep learning, which is a big, interesting field, intersection of two big pillars in machine learning, Bayesian probability theory and deep learning. I'm going to start by just giving a very brief introduction to some of these concepts, just to get everyone on the same page. We're not going to have a lot of equations. I think we're going to have maybe 2 equations in the entire talk. I'm going to start by just covering deep learning. Who knows what deep learning is? Okay, who doesn't know what deep learning is? Okay, no, that's very good. That gives me an opportunity of teaching you deep learning in one slide. Deep learning is built of conceptually very simple models. We basically have, if you give me some data, x and y, x can be images, x1, x2, x2, up to xn are images, and y1 to yn are labels of cat, cat, dog, cat, and so on. I'm going to build a model, which is, I'm going to take a matrix W, I'm going to do an affine transformation. I'm going to take the image x, vectorize that. Just going to do a linear affine transformation, mapping x to w times x, feed it through some squashing nonlinear function, sigma, it can be whatever, we don't care about that for the purpose of this talk. Do another affine transformation with w2, we're going to get some y tilde. For each xi, we're going to get y tilde I, and our task is to find w's for which these y tildes are as close as possible to yi for all I up to n. That's deep learning. In a visual way, you have the vector x that has 4 elements, x1 up to xn. Multiplied by w, we get what we call the feature vector, which is w times x. Multiplied by w2, we get the y output. These are the elements in the y vector. That's also why people call these neural networks, because you can look at these nodes and these linear transformations between some input nodes. Between these nodes and these nodes as edges or as weights connecting these units and these units, these neurons and these neurons and whatever. That's not important. Now, deep learning is very useful. These simple modular tools basically give us these building blocks that we can build, we can compose together to build very, very complex models. The field got huge attention from practitioners and engineers, which in turn built very good software tools, which scale very well with data and compute, and has had real-world impact. So deep learning is being used in lots and lots and lots of applications, but by lots of academics and lots of industry. Deep learning also has lots of issues. For example, we can't really tell what our models know and what they don't know. These are often regarded as uninterpretable black boxes, which are easy to fool, leading to AI safety issues. They lack solid mathematical foundations. Basically, most of the results in the field are based on ad hoc developments. And they crucially rely on big data. Now, some of these problems over here I'm going to talk about tomorrow. Some of these things I'm going to talk about today.
Now, some of this also begin thoughts. This
yeah. So today I'm mostly going to talk about how we can actually use these sort of tools in scientific applications, where we kind of have to get confidence bounds. We kind of have to get stuff that we can actually interpret if it makes sense or not. Stuff that can actually work without having huge amounts of label data. And for a lot of these things, we're going to talk about uncertainty. So what is uncertainty and why do we need it? I'm going to give a very, okay. I'm going to give a very simple and intuitive explanation. So let's say that you have an idea for a new startup. You're going to build a model that classifies different dog breeds. People are going to go online, going to upload a picture of the dog, and that's going to classify which dog breed that is. Somehow you're going to make money out of that, but obviously some user is going to go online and upload this picture of that thing that you've never seen before. Your model has never seen that before. Now, I've never seen that before. I don't know about you, but I wouldn't want my model to force this picture of some object I've never seen before into a specific class of some dog breed, because it's clearly not a dog. It's clearly not something that I've seen before, but I want my model to say I don't know what that is. That's a bit of a contrived example, but we have the same issues appearing again and again in decision making, in physics, in life sciences. Uncertainty can also be used to gain insight into these black boxes when they fail. For example, uncertainty can tell us where am I not certain in my image. So this is actually work that we've done on semantic segmentation autonomous driving, highlighting where the car is looking at its objects, where is it uncertain, where is it confident about its predictions. It can even be used to identify when someone is trying to attack you with the decided examples. I'm going to talk about that tomorrow, not today. And lastly, we need much less label data. If we only label where the model is uncertain. This allows us to avoid wear and tear in robotics, allows us to reduce expert time in medical analysis. We're going to talk about that later today. Second pillar in machine learning is Bayesian probability theory, Bayesian modeling. So the language of uncertainty is probability theory. And specifically, I'm going to talk about Bayesian probability theory that dates back to the 1750s by Reverend Thomas Bayes, nearby actually to Oxford. When you apply Bayesian probability theory to information engineering, we get what we call Bayesian modeling. Where instead of doing maximum likelihood, instead of finding a single set of parameters that maximize the entire probability for the data, we try to find a distribution of all possible parameters, such that conditioning the data, it tells us what parameters are more likely, what parameters are less likely. Or if you think about functions of parameters, you can think about that over here. We have some data points x1, x2, x3, y1, y2, y3. And we have 3 different possible functions that can explain the data. And basically we can say, oh, this is very high probability, this is low probability, this is low probability. So we basically capture a distribution over all the possible models, or over all the possible parameters that can explain the data, rather than just finding a single model that maximizes probability of observing the data, which is what we usually do in maximum likelihood. So Bayesian modeling is built on solid mathematical foundations. Traditionally, it's perceived as fairly orthogonal to deep learning, but I'm going to talk about a very simple way of tying these two things together. Now, I should mention that there's been a huge amount of research in the field over the past few years, and there's a huge number of different ways of tying these things together. I'm going to talk about a very simple one, which is hopefully will be intuitive, and you will be able to get an idea of how we can tie these things together. If you want to look at other recent literature, I would highly recommend going with the Bayesian deep learning workshop webpage from the NIPS workshops from the past couple of years. There's lots of really good research going on in the field. I'm going to talk about one simple way, which is called, which relies on a tool called dropout, which is a very popular technique in deep learning, cited and used millions and millions of times by now. It's not hundreds of times anymore. Should really update the slide. It works very simply by randomly setting network units to 0. So if you remember before, we introduced some notation. We said we have an input vector x that has element 1, 2, 3, 4. All we do now is that when we compute the affine transformation of x times w, we just, first of all, we take x, multiply that by Bernoulli random variables, probability, let's say 0.5, set each element to 0, and then multiply by W. That's all. Then you do the same thing over here. Multiply this by some Bernoulli draws, and then do the affine transformation. That is dropout. At test time, it's a bit different. At test time, you just take normal x times W, and without actually doing any stochasticity. I'm gonna call, when we do the multiplying by Bernoullis by noise, I'm gonna call that a stochastic forward pass compared to the deterministic forward pass, where we just multiply x by W, which is without any stochasticity. This somehow improves performance and reduces overfitting and has lots of other magical properties that I'm not gonna talk about today, but I might mention them tomorrow. And again, it's used in almost all of deep learning. It turns out that we can show that dropout training is identical to approximate inference in Bayesian modeling. And what you're looking at over here is actually a dropout neural network fitting to some couple of data points over here with a bunch of draws from the function, distribution of the function. These are the light black lines, and you can hardly see the uncertainty envelope around it because of the light. So this allows us to connect deep learning and Bayesian probability theory in a principled way. And this mathematically grounded connection gives us a treasure trove of lots of research opportunities, like how to use uncertainty in deep learning, giving us interpretable AI safety approaches, principled extensions to deep learning, I'm going to talk about tomorrow, enabling deep learning with small data domains, we're going to talk about today. First of all, let's try to get an idea for what's going on, like why is that connection even, how does it even make sense? I'm going to go over stuff very high level. So we need to talk about Bayesian neural networks. Who knows what a Bayesian neural network is? Show of hands. Okay, very good. Bayesian neural network is a neural network where we take the weight matrices W that we had before and replace them with stochastic matrices, that's all. So now, basically, we put some prior distribution. We put some distribution over W. Now W is a random matrix rather than being a deterministic matrix. And that's all. That's a Bayesian neural network. Like, if you tell me that W is an variable, that means that I can condition that W on some observed data X and Y. I need to define a likelihood as well, probability of finding Y condition W, but you don't need to worry about that. That's fairly trivial. The main point is that we actually have some distribution over W's, which tells us what W's are more likely, what W's are less likely, conditioned on some data. Main issue is that this thing is very, very difficult to evaluate, and many, many people have tried. We're going to use a very simple approach where we define a simple distribution Q that has some parameter M, and we're going to try to approximate that very complex distribution with this simple distribution Q. So if this is a very complex distribution, and this is our simple distribution with some theta 1, I'm going to wiggle that theta until I manage to match these two distributions together. This is very simple, isn't it? This is called approximate variational inference with pictures. I told you we're not going to have any equations. I don't know if that counts as an equation. It turns out, so if you define Q to be of this structure, which is really not important, with variational parameter M, then the optimization objective for the stochastic variation inference we talked about, without Q distribution, is identical to the objective for dropout neural network, which basically means that if you implement Bayesian neural network with approximate inference with this Q distribution, you will be implementing dropout training line to line in a normal dropout neural network. Like normal TensorFlow, PyTorch, right? But this dropout training is equivalent of implementing approximate inference with this thing, with some important caveats like the probability that you choose, which you can talk about that later if you have specific questions about that. Now what that means, this is like a single equation that I mentioned, is that if you give, actually I don't care about that, I'm going to skip that. What that means is that in practical terms, if you give me a point X, then I'm going to feed that point through the neural network, do a stochastic forward pass. I'm going to get an output Y1. I'm going to feed the same X through the neural network, do another stochastic forward pass. I'm going to get a Y2. I'm going to do that 10 times. I'm going to get Y1 and Y2 up to Y10. Then just going to look at the mean and sample variance for these 10 values. Or in Python, these 4 lines of Python. That's all you need to get uncertainty in deep learning with the small caveats that I mentioned before, like how do you choose the probability for dropout and so on, which actually are important, and we're going to talk about them tomorrow. So what does that uncertainty look like? If you give me the CO2 levels in Mauna Loa, Hawaii, over the past 40 years, I'm going to take that, center that, normalize it, fit a normal neural network, 4 hidden layers, 1,024 units, ReLU activations. You ask me what the CO2 level in 20 years' time will be. I'm going to ask my model. It's going to tell me that. Obviously, that makes no sense. Now, I'm going to take the same neural network, the same fitted model, just like a test time. I'm going to do this thing. I'm going to get that. Now, the prediction over here, 20 years' time, still makes no sense, but the model actually says, I have no idea what's going on. It says it could be anywhere over here. I don't know if you can see that uncertainty envelope, but basically there's 2 standard deviations, basically go all the way from here to here. Basically, model tells us, if you force my hand to give me a prediction, it's going to be here, but it could also be anywhere over here. What can we do with this? You're going to look at 2 examples. You're going to look at deep learning with a human in the loop and deep learning in scientific applications. Okay, we're going to do a complete 180. I'm going to switch to talk about astronomy now. Talked about machine learning so far. This is the Northumberland telescope in Cambridge from 1833. This telescope was donated to the astronomy department by the Duke of Northumberland for the establishment of the new astronomy department. And for a period of time, this was the world's largest refracting telescope. This is a figure from 1840, print from 1843. This is from like a couple of years ago. It still basically looks the same. Fast forward 200 years. This is the Arecibo Observatory in Puerto Rico, 2017. I took this picture last year. This is the control room. This is some stuff where they used to control stuff. This is the primary dish. This is the receiver. That's the transmitter. This is the platform. There's a person walking the platform somewhere over here. It's not this thing. This thing is 4 times the height of the person. Just to give you an idea for the size of the telescopes, how much they increased over a period of about 200 years. What do we do with these telescopes? Well, we do sky surveys. We point them at the sky and collect data. Either targeted sky surveys or untargeted sky surveys. We basically collect lots and lots of data. From that data, we build astronomical catalogs, where we take each target, each source in the image and try basically to find some properties. Is that a galaxy? What's the morphology for the galaxy? How far away it is, and so on. In the olden days, this was fairly easy because you couldn't really see much. So stuff that you could see, you basically take the coordinates and you take the information about that and send it to some journal and say, I found a new planet and stuff like that. As sky surveys became larger and larger, it starts becoming infeasible to do that by hand anymore, and we need to find other approaches. So here comes the Galaxy Zoo project, where they basically use volunteers, citizen science. I think it's one of the largest citizen science projects in the world, where they get volunteers to label astronomical data, astronomical survey data, where they basically take a picture of a galaxy and ask you, is it a smooth galaxy, featured galaxy, and so on and so on. They calibrate the volunteers and use that to collect. They use that basically to build the astronomical catalogs that we use in the field of astronomy. The issue is that even for that, the amount of data that we have these days with the new sky surveys, you don't even need to talk about the square kilometer array sky survey, like even with more than once. Like we don't have enough people to volunteer to label all of that. So what we can do instead, we can use something called active learning. It's a machine learning technique where we collect some label data, we train a model on that labeled data, and then we have a huge set of lots of unlabeled data, lots of images of galaxies that we have no idea what properties they have, but we want to know. So we evaluate something called an acquisition function over that huge pool. So let's say that these are the ones that we do not have labeled data for, these are the ones we don't know. We don't have labels for that, we don't know like the properties that we care about. We train a model over these, and then we use something called an acquisition function over all the unlabeled ones to find which galaxies will be most informative if we did have a label for them. We ask the volunteers to label only the galaxies which are most interesting, according to the acquisition function definition of interestingness. let's say it says this one. We add this one back over here to this label set of labeled data. We retrain the model and then continue the cycle. Yeah, everyone happy with that? Anyone has any questions about active learning? I think that the first question that you should ask is, how do we choose an acquisition function? So we want a function that basically tells us, should take a high value when a point is interesting. What's an interesting point? For example, a point that maximizes uncertainty. But which uncertainty? There are actually different types of uncertainty, which we didn't talk about so far. So for example, aleatoric uncertainty captures the noise inherent in the data. For example, it can come from sensor noise or measurement imprecision. Epistemic uncertainty captures the model's lack of knowledge. For example, because we didn't have labeled data somewhere, or because we had a distribution shift and so on. Some fun facts, aleatoric actually comes from Latin, aleator, dice player, where every time you throw a pair of dice, you will never reduce the stochasticity that you have in the process. You will always have some inherent stochasticity. Epistemic actually comes from Greek, from episteme. Knowledge, it literally means knowledge uncertainty. We have two figures over here depicting these different types of uncertainty. Let's see how much you've been listening. Who thinks that the left one over here has high epistemic uncertainty? Who thinks that the right one has high epistemic uncertainty? Okay, so the right one over here has high epistemic uncertainty because we have some gap in the data where we basically have lots of possible explanations for the function. Basically, if you look at the standard deviation, for example, for this, you take an input point x, do a stochastic forward pass, you get this function, the red one. Take the same point x, do another stochastic forward pass, you sample another function, the green one, and then you get this value. And if you look at the variability for these different values, they're going to be all over the place. We're going to have high epistemic uncertainty over here. Over here, we have high aleatoric uncertainty. Basically, we're very certain what the function is. We just know the function is very noisy. We just know that every time we sample a value from this function, it's going to have lots and lots of noise. For example, I know how the mechanism works, but I also know that I have a measurement error every time I run the mechanism in order to produce an observation. We're actually going to have some examples of that in a few minutes. So to get an idea for which one we actually want to use for active learning, let's say that we want to classify dogs versus cats. You give me some input x. We have three different models, 1, 2, and 3. I feed x for model 1, and I do a bunch of stochastic forward passes, or a sample from the predictive distribution, or another way of saying that I just do drop at the test time and so on. Sample different functions every time. And I get, like we're doing classification, so we're going to get probability for different classes. So I'm going to get 1, 0, 1, 0, 1, 0, 1, 0 every time. I'm going to feed x for model 2. I'm going to get 0.5, 0.5, 0.5, 0.5 every time. I'm going to feed x for model 3. I'm going to get 1, 0, 0, 1, 1, 0, 0, 1. Which model do you think has high epistemic uncertainty? Who thinks that model 1 has high epistemic uncertainty? Who thinks that model 2 has high epistemic uncertainty? Who thinks that model 3 has high epistemic uncertainty? People are very hesitant. So how do we actually capture epistemic uncertainty in classification? That's actually a really good question because this is sort of stuff that is never taught, even in like graduate courses. So let's go back to this picture that we had over here. How do we actually get these probabilities that we just saw in the other slide? So we take a squashing function called, like, for example, a sigmoid that just takes any value between minus infinity and infinity on the y-axis and squashes it to be between 0 and 1. If it's very large negative value, like minus 500, it's going to be squashed to be 0. If it's plus 500, it's going to be squashed to be 1. And that's going to give us, like, for example, like 1, 0, 0, 1 for the different classes. Now, let's say that we have, let's say that this value over here is plus 500. So we take this x, we feed it through the model, we sample a function, we get plus 500. Sample another function, you get plus 500, plus 500. Every time we squash these plus 500s, we're going to get 1, 0, 1, 0, 1, 0. Well, like 0, 1, 0, 1, 0, 1 actually. let's take a point over here now, x over here. We're going to sample one function, it's going to give you plus 500. We're going to sample another function, it's going to give you minus 500, plus 500, minus 500, and so on. Squish v, but when squash v is for the squashing function, I'm going to get 1001, 1001. So basically I get this behavior in this part of the input space. I get this behavior in this part of the input space where I'm very certain and it's going to be very high. And I get this behavior in this part of the input space where I just take an input x, feed it through the function, sample the function, I'm going to get value 0. Squash it, when you feed the value 0 for a sigmoid, you're going to get 0.5. But every time I basically feed the same x, sample a new function, I'm always going to get 0, 0, 0, which is always going to be squashed to be 0.5. So the model actually has a data point over here. There's no point asking for another data point because I already know what the value would be. It will be 0. It will basically be 50-50 for different classes, cat versus dog, or whatever example that we had over here. And actually, for active learning, I want to find these regions to the input space, where actually I have gaps in the data and I have no idea what's going on. So I actually want these things. I want where I have high epistemic uncertainty. I'm going to skip this slide. So we're going to take these same ideas we talked about and actually apply them in astronomy. So this is a joint project with Louis Smith, Mike Wormsey, Chris Lintert, and the Zooniverse citizen science team that was just recently accepted to the Royal Astronomical Society, where we literally take the same ideas we talked about and apply that to the Galaxy Zoo citizen science project. Where instead of using volunteers to just get the astronomical catalogs, we use volunteers to label where the model doesn't know, and then retrain the model, and then ask volunteers again, now I have a new thing I haven't seen before, can you please tell me what that is? Is that interesting? Is that something that I've seen before? I'm not going to bother asking a volunteer to label that. We actually have some pretty interesting results. So I have two plots over here. On the x-axis, we have the acquisitions, the amount of data that we ask the volunteers to label, basically, amount of images that we went over in the pool set, asking volunteers to label. First plot, on the y-axis, we have the amount of the training loss, so basically the amount of surprise that the model has whenever you see data that you've never seen before. If you have new data that you've never seen before, you're going to be very surprised, you're going to jump up. Second plot, we have in the y-axis, we have the evaluation performance on a set-aside dataset, validation dataset that the model hasn't seen before and is not using in order to decide what data to get labeled. We have two different plots. We have two different graphs over here. We have a baseline, which is just this orange one. Just randomly select a galaxy from the pool set, probability with uniform probability, and get a volunteer to label that, which is literally what we've been doing, what the team has been doing before. And the blue one is the active learning one, where you actively seek points that you think that you will be surprised about, you think that you will be confused about, you have high uncertainty about. So you can see the blue one, like when you just randomly select points from the dataset, most of the galaxies kind of look the same. You're most likely to select a point that you've already got labeled before, so the model is very unlikely to actually be surprised with any new data. Therefore, like the baseline just goes down and kind of stays down, whereas active learning keeps getting surprised every single time because we actively seek points that the model has never seen before. And in terms of data efficiency, they have some threshold. I don't know how they got this threshold of 0.12, but for this different threshold, for this threshold of evaluation RMSU that they wanted, you basically had to get half the amount of labeled data than if you were to just randomly select stuff from the data set. So basically, you need half the amount of volunteer hours in order to get the same performance. So that's really neat because you basically free up a lot of time from volunteers that can be used for other scientific applications. Okay, so this was one example application in astronomy. Any questions so far? Otherwise, I'm going to skip to the next application. Everyone very happy with that? Actually, no, I have another slide over here, which is actually very interesting. So if you look at the type of different data, so over here we have smooth versus featured type of data. then the random acquisition just samples based on the frequency in the data set. So most galaxies are just very smooth, i.e. very much not interesting. And it just like takes that, and the active learning actively avoids these and looks for the non-smooth ones because you already got enough of the smooth ones. Next application. So meet WASP-12b. WASP-12b is an exoplanet orbiting the star WASP-12. It was discovered in April 2008. Its distance is 1,410 light years away from us. And working with the Hubble telescope, scientists recently reported detecting water in the atmosphere of the exoplanet. Now, a very interesting question that you might ask is, how can we tell that there's water on this exoplanet, which is 1,410 light years away? And the answer is, we use the Hubble telescope to basically to look at the spectrum for the exoplanet. And what we do is we basically say, well, if we had certain atmospheric parameters, if the atmosphere were composed of certain concentrations of different compounds, we kind of know the forward model. We know how physics works. So we know how to map, we know what the spectrum should look like for certain atmospheric parameters. So what we do, well, what the basically scientific community does in practice is fiddle with these atmospheric parameters until they manage to generate a spectrum that looks similar to the one that we got from the from Hubble. When I say fiddle with the parameters, I basically mean using nested Monte Carlo MCMC, which takes a few hours to do that for a single spectrum, but MCMC is basically fiddling with the parameters, isn't it? This has some issues because, as you can imagine, it doesn't really scale as you start seeing more and more exoplanets, especially if it takes hours and hours to do each modeling. So instead of that, we can try to learn an inverse model. We're going to generate lots of possible atmospheres. We're going to basically sample lots of possible atmospheres, feed them through the forward model, generate what the spectrum should look like. We're going to train a neural network to map backwards from the spectrum to the atmospheres. Now, we have observation noise in the forward model. We actually know that we have systematic noise in the lens for Hubble and so on and so on. So we actually know that this forward model is very noisy. So we know that the mapping from spectrum to atmosphere is going to be noisy as well. And more interesting, we know that if you observe a spectrum which wasn't in the training set, we must be able to indicate that. We don't want to say, oh, there's definitely water on that exoplanet, even though it's just extrapolating confidently to stuff that we've never seen before, which neural networks really like doing. So what we did in this project was use the same ideas from Bayesian neural networks, and basically build a model that takes the spectra in, uses a bunch of layers of concrete dropout, which I'm going to talk about tomorrow, and spits out the mean and the covariance for the atmospheric parameters. So this basically allows us to have capture structured correlations in the dependence of the different composition in the different atmospheric parameters, and tell us how confident we are about our predictions, where we basically integrate, we have uncertainty over L as well. So how do we know if you're actually doing well over here or not? We start by generating lots of synthetic data, the one that we use to do this thing. We set aside the validation set, and then we look at how well, by just taking the validation set, we take the spectrum, feed it through the model, and look at the atmospheric parameters it spits out, and see whether they actually correspond to the ground truth synthetic atmospheric parameters. We can see that generally they correlate quite well, and we can actually see the distribution of the different parameters versus other parameters. I'm going to skip that. I think this is more interesting. So this is actually applying the same model to WASP-12b, where we can actually see that the model actually captures the posterior correlations. So I think what they call that posterior correlations, we call that predictive probabilities. But we capture the posterior correlations between the different atmospheric compounds, and we can actually see that we have water over here. So I think this is a really neat application. So this was done with Adam Korb and others as part of NASA FDL and together with NASA Goddard, and this was published recently at the Astronomical Journal. I'm going to talk about last application. We don't have a lot of time left. I'm going to talk about applying machine learning literally in space. So I'm not going to, this is like bigger than, we're not really talking about Bayesian deep learning anymore. I'm just going to talk about machine learning generally. And specifically, I'm going to talk about flood detection. So this was work done with Louis Smith and collaborators and ESA as part of FDL Europe. So floods are becoming a bigger and bigger problem, a bigger and bigger concern, especially with shifts with shifts that we have in global weather, and basically being able to get to first responders and give them accurate maps of where we have a flood is becoming extremely important to be able to give a very quick first response. I think, as far as I remember, I think that in some cases, actually, yeah. So this is like an example of like the so this is an example of the sort of stuff that first responders basically usually appreciate, which is having a map of where we have water or not. So this is an example between a comparison between like unflooded area and flooded area, and you can see how difficult it is to actually tell whether where we have water or not. Over here you can see we have water. Over here I think we have water as well. Over here there is no water. Basically, what first responders need is a map, flood map, of where we have areas underwater. Based on that, they can prioritize where they should send help and how which places need more urgent help than other regions. The issue is that the current way that we produce these flood maps is actually fairly inefficient. We have to query a telescope, so we have to query a satellite, commission satellite time. Usually there's for in case of emergencies, you can basically get that fairly quickly. But then you need to wait until the satellite actually goes over the flooded area. You need to wait for the satellite to go over the ground station. You can send all of the data down, and then you need to get all the data processed. You need to get a data scientist to sit there and process the data and clean it up and decide this is flooded or not, and then send it back to the first responders. And over here, we basically looked at how can we automate or accelerate this process with this pipeline to be a bit more efficient. What we looked at specifically is, can we actually do the flood detection on board of the satellite itself? Because that actually saves us a lot of the hassle of a lot of these different issues we talked about. We don't need to wait for a long time in order to, so basically if you have a constellation of CubeSats, for example, then you don't need to wait a long time in order to get a CubeSat going over the area of interest. You can actually use an antenna in the field to basically communicate with a CubeSat. And basically, the biggest bottleneck that we have, if we do actually want to do the flood detection on the CubeSat, is that we usually have very noisy observations. We usually have very limited compute because we have very small amount of power as well. And we usually have very small bandwidth to actually send all the data back down because they are much, much smaller, and we don't have these huge antennas on these CubeSats. So nice thing is that if you actually do the segmentation of the CubeSat, then we actually just need to send yes, no, one binary bit for each pixel. Do we actually have water over there or not? We don't need to send the entire raw data. We just need to send it also for a targeted region. So we can actually reduce the amount of data that we need to transmit a lot. And the main questions that we basically have are, can we actually get that to perform well on the CubeSat? So in this project, we actually so this is stuff that we just finished a few months ago. And managed to demonstrate that using model compression and pruning techniques, we can actually get these large segmentation models to work on a CubeSat under the power consumption constraints that we have. Specifically, I think these CubeSats are using, so this is part of the FISAT-1 FCSS mission using Intel Movidius Myriad 1 chips, where we actually can get these large computer vision models working on the CubeSat itself, doing the segmentation. And the idea is basically to launch that on the CubeSat in early 2020 now, because I think they had some issues with the Vega 16 rocket. And actually test whether we can actually get to first responders much, much faster than otherwise with the existing pipelines. Yeah, so this was the last application. Actually, I think there's lots of more research, interesting research that could be done, like developing new tools that help others build safe and robust machine learning for responsible deployment in industry, in academia. There's lots of stuff on autonomous driving, which I didn't talk at all about. We have applications in medical domain, like we're working with the guys in Montreal and CMU on brain tumor segmentation, safe reinforcement learning, and much, much more. All of the work that I showed was done by the guys from my group, so thank you very much for everyone over here, and thank you very much for listening.
Questions?
Mm-hmm.
For using dropout during inference to evaluate the variance parameters of the output, I guess that you have some threshold in the dropout rate, right? Because if you do too much dropout, then you lose the network capacity. How do you cope with that? I mean, how much is too much?
So the question was about basically how do you choose the dropout probability, which is a very important question, which I mentioned. That is basically the main caveat that I mentioned before. When I said there's a big caveat into actually, you can always just choose some model that has some dropout and do some stochastic forward passes. It doesn't mean that you're going to get uncertainty that makes sense. To actually get uncertainty that makes sense, is calibrated according to the definition of calibration, that in context of like getting improving downstream performance for these different tasks that we talked about, then you actually need to be very careful about how you choose that probability. You need to use the same probability at test time as well as at training time. Easiest way of choosing that is by just doing grid search. So we just set p equals 0.5, 0.4, 0.2, 0.1, and just see how much it affects the uncertainty and the quality of the uncertainty in the actual application that you care about. What we're going to talk about tomorrow is actually how to tune that automatically, because that is actually, when you think about how can I tune that automatically, that actually becomes a very difficult question, very much non-intuitive question. Because when you ask, what do I tune it with, like what do I need to tune? What objective do I need to actually optimize when I wiggle these parameters for the dropout probability? So that's actually stuff we're going to talk about tomorrow. If there are no other questions, then thank you again.